Okay, so I'm going to talk about the electric current control of structure and the physical properties in some 4D and 5D transition metal oxides. So first, I'm going to give you a very brief review, emphasizing some of the relevant features of these materials, and also I'll give you two examples. One is 5D transition metal oxides, strontium-2 iridium-04. The other is 4D transition metal oxide, calcium-2 ruthenium-04. And I was hoping that Miano could talk about this, but he canceled his talk, so I need to do some introduction later on. So then I will finish my talk with this with a summary. So this cartoon picture actually highlights the essence of this topic. That is, for some of the 4D and 5D insulators, if we have a structural distortion, such as this, then if you apply electric current to the system, so the result is that the electric current can actually relax distortion and manipulate crystal structure, therefore physical properties. So that's actually is the central point of this talk. So I'd like to remind you a few things. This is 4D and 5D transition metal oxides. So the atomic number is high, relatively high. We know well that the spin orbital interactions are proportional to atomic number. So therefore, in these class of materials, for instance, particularly 5D transition metal oxides, the spin orbit interactions are actually quite strong. Here, you can see that this is close to 1 electron volt, and it's about 10 times larger than that of 3D electrons. And then also, these are the materials that have extended orbitals. So therefore, the Coulomb interactions are largely reduced. So for instance, here for 5Ds particularly, the Coulomb interaction is largely reduced compared to, say, U for 3Ds. But then these Coulomb interactions for 5Ds, and even to some extent 4Ds, are very comparable to the spin orbit interactions. And then the other one is the Holmes-Rowe couplings. We have some discussions early this morning. Holmes-Rowe couplings also get smaller as we move from 3D to 5Ds. So the point here is to emphasize a new balance between relevant energies. Okay, so that is here for 4D and 5Ds, particularly for 5D oxides. There we have this comparable energies. So therefore, we have a new balance, and this new balance actually drives new physics. And then this is something that I like to talk about a little bit in the next in the remaining the time of this talk. So let me give you a few experimental observations as well. So for instance, for ruthenides, this is something that we have some discussion early this morning. If we are looking at the Rodstam-Popper series or layered ruthenides, so for strontium ruthenides, they are all tend to be ferromagnetic, and then they are all showing metallic behavior. And then we understand that some of these the resistivity at the high temperature is way beyond limit, but then the behavior is more or less metallic. But then if you replace strontium here by calcium, and their calcium have the identical valence state, but then it's 20% smaller compared to, in terms of the ionic radius compared to strontium. So what happens is completely different ground states. Here, for all these calcium ruthenides, they tend to be antiferromagnetic, and then they tend to show insulating state with metal insulated transition. So actually, for one of these compounds that's showing these transition at 357 Kelvin is the one that we're going to talk about. This is a single layered calcium-2 ruthenium-04. So the point here is that in this type of materials, when the orbitals are extended, so they are extremely sensitive to the lattice modification. So in other words, we can drive physical properties by changing lattice parameters or lattice. So this is some of the underlying features of ruthenates. For iridates, we have a few things to say. That this is again, this is empirical trends or observations in these materials. So iridates tend to be magnetic insulating, and then this is actually was very puzzling when we started this study in mid-90s, because as we said earlier, that the iridates, they have this 5D electrons, and they should have extended orbitals. So we should expect the system to be less correlated and less insulating, less magnetic, and more metallic. But then with a couple of exceptions, almost all iridates are magnetically ordered and insulating. Right? And then also there is unusual correlation between magnetic and the insulating states. This is something that I'll come back later. And then one other outstanding feature is that these materials do not metallize easily at high pressure. So recently we did a high pressure study on this compound, strontium-2 iridium-04, and then we applied pressure up to 185 GPa, and the insulating states actually persisted. So we think this persistent insulating state suggests the importance of crystal or structural distortion, despite the large band broadening under high pressure. But on the other hand, the system can be, metallic state can be readily realized if we dope chemical impurities to the systems. Okay, any chemical impurity doping in this system and the other iridates very often can induce the metallic state. And yet the superconductivity remains unconfirmed despite the similarities to cuprates. And more generally, there's growing lists of theoretical predictions or proposals, spin liquids, such as spin liquid, various topological states, superconductivity, et cetera, et cetera. But then they have met very limited experimental confirmation. So we think this large, the discrepancy is actually in part is due to this type of materials are extremely sensitive to disorder and the structure distortions. I think this is one of the major feature of the systems, and it's something that we do not often see in other materials. For instance, the 3D oxides, 3D transition metal oxides. So this is certainly a challenge for this type of study, but then also this type of feature gives us some advantage. So that is, again, we can control physical properties by controlling lattice. And then one other important feature in this type of materials is that there is a strong interlocking between the lattice and the magnetic moments. Okay, so we take advantage of these features, and so in the rest of this talk, I'm going to give you two examples of current control phenomena. So one is this compound. It is well known, and one of the major structure feature of this compound is this octahedral rotation about the c-axis by about 12 degrees. Okay, so this is a too busy picture, but then you will see that there is rotation here. There's no tilting in this compound. And then later on, neutron diffraction results also observed that the magnetic moments are also deviate from EZ axis, which is A axis, by about a similar degree, which is about 13 degrees at 4 Kelvin. And then later on, the other experimental result study also indicating, so there is this strong coupling between structure rotation and the magnetic canting. So this is one of the major feature in iridates, and particularly for this compound. The underlying properties of this compound is that it is magnetic. The magnetization showing this magnetic order at about 240 Kelvin. We initially labeled this TC because we thought this is a ferromagnetic. But now, nowadays, the neutron data in recent years indicating that ground state actually is antiferromagnetic. And it is insulating. And then one thing that I'd like to point out, I pointed out earlier, that is, there is no corresponding anomaly corresponding to this magnetic order. So this is something that is very different from things that we've seen in other 3D materials, for instance. Okay. And then this study, this current control study, to some extent, is actually our continuation of early studies. So we started these studies, this 4D and 5D transition metal studies in 90s. So one thing that is very that was very puzzling, still is puzzling, that is, these materials tend to show very unusual IV curves. So for instance, this 2 says this is a strontium to uranium-04 that's showing this very unusual IV curves. Similarly, calcium-3 or ruthenium-02, the 7 should be down there. Also is showing this type of behavior. So it was very puzzling why the things is like this. So in recent years, we decided to revisit this type of issues. So we started to think that what currents can do to structures. So in order to do this, we actually designed this setup here. This is our single crystal X-ray diffractometer. And then this is the sample holder. On tip of this, there was a sample. The sample is about 70 micron. And then on this sample, we have 2 very thin gold leads attached to the sample. And then this golden leads and are connected to the thicker copper wires, and the copper wires go to the current source. So what we can do is that we can do X-ray diffraction, single crystal X-ray diffraction as a function of current. And also we have this temperature control here. So we can also run the temperature, run diffraction as a function of temperature. So we have 2 parameters that we can change. So one is current, the other is temperature. Our initial, results actually are very encouraging. For instance, this is a set of black peaks. So let's look at this one. So without current, this may be too small for you to see. Without current, we have this very bright peak here in this position. And then the intensity is about 3,000 counts. But then if we turn on the current, then not only this spot moved, but also intensity is largely reduced from 3,000 to 900. So this is very encouraging. So that means that the electron actually can do something to lattice. So then we decided to do more thorough investigation on this matter. So these, so forget about this for the time being. Okay, so just look at this box. These red curves are the A-axis expansion due to application of current. Whereas these black curves are magnetization for reference. So the results here indicating that when we apply current to this system, lattice, in this case, A lattice, actually expanded very significantly. So around this magnetic order, 240, we'll have this peak here. So this indicating that actually A-axis expanded by about 1%. And of course, and the C-axis remains essentially unchanged. So of course, we are mindful that whenever you apply current, heating is always an issue. So we want to make sure that this is not something due to just self-heating. So we decided to do other compound. So this compound is that we have this 3% terbium doped on the iridium sides. So what this doping does is completely suppress the long-range magnetic order, and yet retains the insulating state and the crystal structure. So we did exactly the same measurements. So this is what we see here. So this is the A-axis, this is the C-axis expansion. So you can see that the expansion is very, very small. So this gives us some confidence that this type of behavior that we've seen maybe is intrinsic. But of course, we want to make sure everything is in order. So we also measured the thermal expansion for the same compound, for the same materials. So we did it from 90 Kelvin to 300 Kelvin. So without current. So we just want to see what is the thermal expansion if it's self-heating. So here, the thermal expansion is at the most about 0.1%. So compared to this, it is about 1%, so 3 times smaller. So this gives us more confidence that indicating indeed there is something going on in the in this structure when we apply electric current. We want to make sure everything is right. So we also did more current measurements. So this time we made sure that current is applied along the A-axis. And then we measure A-axis expansion. And then this is what happens. And then this expansion happens around 240 Kelvin. That's no temperature. And then at the same time, we apply current to C-axis, and then there's not much going on here. So recall that the moments, the magnetic moments are actually within, there's some canting there, but then are within AB plane. So this result actually is reasonable. So that means the current is somehow engaged with the lattice, and the lattice in turn coupled with moments. This is an X-ray diffraction in-house. And then sometimes bond angle cannot be accurately determined. So we also did the neutron diffraction at the Oak Ridge. So this is the setup. Okay, this is just examples there. So what we see here is this. This is the oxygen-iridium bond angles. So as we said earlier, that one of the important structural feature of this compound is the octahedral rotation about the C-axis by about 12 Kelvin. And then an old study indicating that this rotation actually is very critical to the physical properties, transport properties, magnetic properties, etc. So here, without current, here we see this anomaly near this no temperature. So this is reasonable. But then if you apply current, so this anomaly disappeared. Okay, so this is another piece of evidence indicating that the current can indeed modify the crystal structures. So the rest, actually, the other slides that I'm going to show you won't be that surprising anymore, because we know for this type of materials, lattice plays a critical role. So if you change lattice, of course, you can change a lot of things. So for instance, here, this is a magnetic susceptibility as a function of temperature at the different currents. So you can see that this magnetic order decreases systematically with increasing current. Here, this is the derivative of that to show you. So this indeed is decreasing very rapidly. And if we measure this, so we also measure isothermal magnetization here with current. So we also see the magnetization drops by 16% at about 100 milliamps. So all this behavior, we argue, is because that current, when we apply, this is a no temperature, and this is magnetization. This is the data coming from these two sets of data. So all these changes actually ultimately is because the current, applied current, relax the crystal structure and actually reduced magnetic canting. Therefore, we see everything here. So reduced no temperature, reduced magnetization. Yes. Oh, all right. I gotta be quick. I only have 5 minutes. I have another system. Okay. So this is the IV curve. The IV curve we measured again. Now we think we have some understanding of that. There is a threshold here. For instance, there's a turning point here. So we compiled all these turning points in this data, and also compare these turning points, these thresholds with magnetization. We see that there is this red dots at the thresholds. There is a big break near the temperature where we have magnetic anomaly. This is not phase transition, but our recent study indicating that there is actually significant lattice change. And also, when you increase current, the resistivity drops, especially at low temperature. At one point, that we have this transient metallic behavior at low temperatures. My time is running out, so I need to go a little bit faster. So in order to go back to our initial motivation to study this, so this is the IV curve, and then this is the A-axis expansion. So now we have some understanding of this unusual IV curve now. So you can see when we put everything together here, we see that the IV curves closely track the current control A-axis expansion. So let me highlight this here. So here. So I think this, so we argue this might be one of the main reasons that we are having this type of behavior. And then more generally, so when the structure is getting more relaxed, of course, resistivity, the electron gets more mobile, so therefore resistivity drops, and so on and so forth. So I'm running out of time, so I have one more case to show, but then I want to show you some some of the important slides. I was hoping that the Miano's talk could give us some background. So, but then fortunately, I'm sure that we know this compound very well. So there's two important temperatures. One is this very violent first order transition that happens at the 357 Kelvin. The other is the at very low temperature, lower temperature, we have an antiferromagnetic order. Okay, this transition is very violent. So in order for us to do a thorough study, so we doped some impurities in the systems. But this doping does not change anything, does not change underlying properties of these materials. So this is neutron diffraction data. And this is the temperature, this is the A-axis and the B-axis. As you can see, that without current, we have this split in AB. So in other words, there is a strong orthorhombicity. But as we apply current, this orthorhombicity actually is reduced. Without going through too much details, let me just give you the summary of the structure. So what's important, what is happening here in structure is that when we apply current, this is A-axis and B-axis. So what's important, the important observation here is that orthorhombicity is largely reduced. So this is the cartoon illustrating that. And also at the same time, C-axis is elongated. So this again is cartoon. And then more importantly, here, all these rotation angles, tilting angles are all relaxed, okay? So then the rest is actually is expected. So this is magnetization when current is applied along the B-axis. This current can systematically suppress magnetic order for both directions. And then simultaneously, we'll also measure the resistivity, and the resistivity drops by several orders of magnitude. So this happens at the current, that is small current. The density of the current density is about 0.15 amps per centimeter square. But then when we are going higher, the higher current density, then what we see is this, is that the native long range order disappeared. But then what happens, there is a new order that emerge. And then we don't know the nature of this yet. But then certainly we see corresponding behavior here in magnetization and also resistivity. So in order, again, because this data is taken on an impurity doped sample, so in order to rule out the possibility of this is doping effect, so we also managed to measure pure sample. So at a higher current, so what we see is similar to this. So we believe this is something that is intrinsic to this calcium 214 compound. Okay. One other point that I want to point out is that this is an orthorhombicity and this is a resistivity as a function of temperature and also current density. You can see this patterns are almost exactly identical. So therefore, we have this conclusion that is everything here is driven by this by the structure change. This is a phase diagram. So what I want to point out is that at the lower current, the native antiferromagnetic order suppresses and vanishes at this critical point. And right after this, there is another order emerged. And the nature of this is still not so well understood because this involves non-equilibrium state. So, but then one thing that is clear, we do not see diamagnetic response that is reported earlier by Japanese group. Okay, I know my time is out, so I'm going to stop here. I have some summary here, but then we can talk about this if there's any questions. Okay, and I certainly like to acknowledge my co-workers. Yeah.
Thank you very much. Time for questions. Do we have any questions locally? Yes, please. Why don't you come up here and speak directly to the microphone?
Okay. Here?
This is the microphone.
Okay. All right. Thank you. My question is, the current densities are quite substantial. So I wonder if there are hysteresis effects and if you characterize them.
Yes. Oh, yes. Okay. Yes, there is. You're saying the hysteresis effect, right? Yeah, there is a very strong hysteresis effect when current is beyond the, for instance, for this calcium-2 systems. So in this region, in this region, the hysteresis is very, very strong. It's so strong that the relaxation time could be a few days. So we really don't understand what's really going on there. But then below this, the hysteresis behavior is very weak. Yeah.
I just wondered if this behavior has anything in common with what's seen in sliding charge density wave systems. Since it's an anti-ferromagnet, it also has a charge density wave. So
yes. Okay. This is a good point, and then there is such a suggestion, but then so far we haven't invested a lot of time on this issue. But then there are some suggestions like that. Yes, I think this is a very reasonable possibility. Yeah.
Other questions from the audience? So if not, let me ask explicitly: is there anything from any of the other rooms?
Been not here for like 2 weeks, man.
Most of the crowd here has moved to a different room and is not with me, so I can't answer. I don't have a question.
Okay, and I have a chat window open, but there's nobody who is asking any questions. So in that case, I suggest we thank the speaker again.
Thank you.
Yeah.